Welcome to this video series, Machine Learning from Fundamentals. In this series, we will explore what machine learning really is, what we mean by data, and we will dive into why neural network architectures work the way they do. We will discuss the challenges that lie ahead, how the future of machine learning, deep learning, generative neural networks is shaping up, and why it's unfolding the way it is. Everything will be explained through a clear, logical framework designed to be accessible and engaging for all audiences, regardless of your background. Everything around us is data, whether we talk about optical camera that absorbs the electromagnetic light waves and converts into a red, green, blue RGB image that we see on our mobile screens or on our computers. Or we talk about sound waves, which is a pressure wave that moves from one point in space to another point and causes a movement of energy, which our ear has evolved over millions of years to sense that movement of energy in a form of a pressure wave and convert that information into what we call an audio information. Similarly, there are other types of phenomena in the nature. For example, heat flow. The laws of thermodynamics govern how the heat flows in our surroundings. Uh, whether we talk about gravitational forces, which is a very weak, very long range force, different types of wave propagation, wave phenomena, or we can even include those high level abstract notions about how emotions or feelings or other similar abstract phenomena, how do they travel. So in simple words, at a high level, movement of energy or mass in space-time from point A to point B is what produces data. And machine learning, deep learning, any type of neural network that we talk about, data is mainly at the core of all of these technologies. So we need to really understand what does data mean and all the different modalities of data that we talk about. After defining what data is, the next thing is to understand what kind of data interests human beings. So we have these five sensory organs. Our eyes perceive the physical world around us, and we have our ears. We can sense the sound waves. Our brain can interpret the message in in those sound waves for those particular frequency ranges for which our ears are sensitive to. Then we have this sense of taste, sense of smell, and this sense of touch. Uh, so let's talk about eyes. So human eyes and adults' eyes typically perceive like 12 to 15 images per second. So if we say if a person is awake 14 hours a day, at 12 to 15 images per day, typically for 14 hours, the total number of images that our eyes see throughout the day in one single day is close to 7 to 800,000 images. So our main source of data or information to our brain is through our eyes. And it's amazing that our brain consumes like 60 watt of energy, and throughout the day it can kind of perceive close to a million images. So the biggest chunk of information that reaches to our brain is through our eyes. uh, let's say typically around like 90% or more than that. Then a small chunk is sound. Then we have like even smaller contribution from other sensory organs like taste, smell, and touch. There are other modalities of data in digital data, analog data, but ultimately that chunk is also mainly to understand or to help us better understand the physical world around us. Another better interpretation to understand this, why I'm saying that almost all the information to our brain is coming from our eyes, is that uh, during our day hours, when a human being is awake, we can sit for like continuously for hours without any sound, without eating anything or smelling anything. But it's very difficult for a human inquisitive human brain to sit idle with our eyes shut. So, this is another indirect way to understand that our brain actually is always very hungry of the main source of data or information that is coming through our eyes. Let's do another interesting calculation. Let's say if roughly our brain consumes 60 watt of power. So let's say if we are awake for 14 hours. Uh, so typically the energy consumption for 14 hours is less than 1 kilowatt hour. Uh, and on the other hand, so our brain consumes less than 1 kilowatt hour of energy to interpret close to a 1 million images. Whereas on the other hand, if we see stable diffusion or these new advanced architectures to interpret uh, images and generate images, so those neural networks actually do billions and billions of uh, floating point calculations in a computer to just understand and perceive one image, which is very energy inefficient. Uh, you might have heard in news that these days, like the power consumption is easily in coming years is going to like hundreds of megawatts to even more than gigawatt for these large language models or large image processing neural networks. So this is extremely today's framework, today's infrastructure, or today's neural networks are highly energy inefficient in the way they process the information or the data today, especially in the visual domain. So at a high level, the goal is to understand and perceive the world around us, because once we understand and perceive the world, then it's easier to adapt it or modify it to make our life further easy. And that has been, whether we talk about industrialization, whether we talk about uh, every human innovation over the last centuries, the main purpose is to contribute to our productivity and make our lives more easier. Uh, the same is the goal with the data here. So we have a lot of these sensors, cameras, audio devices, millions of other sensors. And the goal is to collect this data, which provides information about the world we live in. And then what we want to do is we want to learn patterns from this data. We want to learn interesting things that exist in this data. So, for example, in this image, let's say we have a image captured by an optical device or a camera. It's an RGB image. If we see, it's just a three-dimensional, a bunch of matrix with numbers that tells us intensity at each and every pixel of a particular location on this XY grid on this image. Uh, and what we want to do is we want to learn some interesting patterns in these numbers such that they can uniquely help us identify that there is a particular object of interest in this image, as in this example. Uh, so similarly, the goal is to perceive interesting, useful information in the data from our surroundings, to understand and then to make a better use of that information to update or improve our world. Data is everywhere, it's all around us, it's being generated at every instance of time. And the purest form of information is coming from this raw data that exists in the nature. So, for example, coming back to this original image that we had on the previous slide of optical camera. Uh, so, optical camera works on the principle that it collects the electromagnetic or the visible light that is scattered from the object of interest. A lens captures that light. There are some analog and digital steps that convert this visible light, which is coming into the camera lens and is the purest form of information, into an RGB image, which is stored, let's say, somewhere in our temporary or permanent memory or some buffer on our computer. This information is then used to interpret what is there in that particular image. Uh, there are a lot of, you can see in this image, a series of different analog and digital processing steps that converts that visible light, ordinary light, to an RGB image. And since all of these steps are a kind of transformations, so we are actually using or modifying the information, the purest form of the information that we have in all of these steps. For example, we have these RGB filters that filters out the light into a particular, focuses the light of RGB colors to particular CMOS sensor arrays, uh, which is a photo detector that converts light intensity into electrical signal. And this electrical signal is typically very weak signal, millivolts or even lesser than that. Uh, and this very weak signal is then amplified using some analog circuitry. After that, we have analog to uh, digital conversion, which is a lossy conversion. So we use some information during this process. And after that, we have image processor and buffer that finally converts into a number array or the matrix of number that we see as an image in our computer. So these transformations, analog and digital, although the time probably is in milliseconds or microseconds for many of these steps, but it does take some time, and it does. We do use some amount of information from the purest form of information that is at the input. Uh, so one of the things is how to reduce, for example, these days, if you must be hearing a lot about inference frameworks, inference architectures, how machine learning, deep learning is going in each and every device that we use. It's becoming an essential part of our everyday life. So we are typically doing hundreds and thousands of inferences every day, whether we are doing Google search, whether we are asking some queries to some of these chatbots, and it's going to be becoming more and more evident. So with every inference, so one of the core ideas, whether it's training or inference, is to see how we can reduce the number of these pre-processing steps, because one of the historical reasons of these pre-processing steps is uh, to make it interpretable for humans, and also to make it uh, digital so that it can be stored on a computer. The part on the need of a digital usage by computers is still there, but can we think of or improve how this purest form of information can be directly fed into a neural network uh, to learn from the purest form of information without modifying it, and learning the patterns from this better form of information. This availability of data and the need for learning the interesting patterns in that data uh, is growing, and it's going in every walk of our life. And based on this particular need and availability of different types of data, we have these three different categories of how we classify different algorithms that fall into the domain of machine learning and deep learning. But everything originates from the data and the need of learning patterns in the data, and also how abundant we have different forms of data. So we will talk about these three different categories of data and the landscape of machine learning that has come up because of that.